Hello everyone. Am I audible? Please reply if I'm audible. Please reply if I'm audible. So very quickly we can start. Okay. So as per the request of one of the viewers, we start with this chapter, reading of the chapter 10 Standard ICSE, chapter number 3, machines. Of course, physics. So we start with this machines, the technical terms and the levers. Machines. It is a common experience that it is easier to open a nut by the use of a wrench than to open it by the hand. It is difficult to pull up a bucket of water directly from a well, but it becomes much easier to pull it up with the use of a pulley. It is difficult to shift a heavy block by pushing it, but it becomes easier to shift it by using a crowbar. We can find many such examples in our daily life where the use of a machine such as a wrench, pulley, crowbar, etc. makes the job easier. Functions and the uses of simple machines. The various functions of machines are useful to us in the following four ways. First, in lifting a heavy load by applying the less effort, that is, as a force multiplier. Examples: a jack is used to lift a car, a bar is used to lift a heavy stone, a spade is used to turn the soil, pulleys are used to lift a heavy load. In all these examples, the effort is much less than the load, so the machine acts as a force multiplier. Second, in changing the point of application of effort to a convenient point. Example, the rear wheel of a cycle is rotated with the help of a chain joined to a toothed wheel by applying the effort on the pedal attached with it. Thus, the point of application of effort is changed from the rear wheel to the pedal. Of effort to a convenient direction. If a bucket full of water is lifted up from a well without the use of a pulley, effort has to be applied upwards. By using a single fixed pulley, it becomes possible to lift the bucket from the well by applying the effort in the downward direction instead of applying it upwards, so that the person lifting it up may also use his own weight as an effort. Fourth, for obtaining a gain in speed, that is, a greater movement of load by a smaller movement of effort. Examples: when a pair of scissors is used to cut the cloth, its blades move longer on cloth while its handles move a little. Second, the blade of a knife moves longer by small displacement of its handle. Here, the effort is more than the load. Hence, we define a machine as below. A machine is a device by which we can either overcome a large resistive force or load at some point by applying a small force or effort at a convenient point and in a desired direction, or by which we can obtain a gain in speed. Note: a machine cannot be used as a force multiplier as well as a speed multiplier simultaneously. Let's understand the technical terms related to a machine. First, load. The resistive or opposing force to be overcome by a machine is called as a load. Second, effort. The force applied on the machine to overcome the load is called as the effort. Third, mechanical advantage, MA. The ratio of the load to the effort is called as the mechanical advantage of the machine. That is, mechanical advantage is equal to load upon effort, that is L upon E. While using a machine to overcome a certain load, if the effort needed is less than the load, the machine has a mechanical advantage greater than 1, while if it needs an effort greater than the load, it has a mechanical advantage less than 1. A machine has a mechanical advantage equal to 1 if the effort needed is equal to the load. A machine having the mechanical advantage greater than 1 acts as a force multiplier, while the machine having the mechanical advantage less than 1 gives the gain in speed. The machine having the mechanical advantage equal to 1 is generally used to change the direction of effort, as there is no gain in the force or speed. Unit. Since mechanical advantage is the ratio of two similar quantities, so it has no unit. Keep this in mind. Mechanical advantage has no unit because it is the ratio of two similar quantities. Coming to the next, that is velocity ratio, that is VR. The ratio of the velocity of effort to the velocity of load is called the velocity ratio of the machine. That is VR, that is velocity ratio, is equal to velocity of effort, that is VE, upon velocity of load, that is VL. If DL and DE are the distances moved in same time, T, by the load and the effort respectively, then velocity of load VL is equal to DL upon T. Velocity of effort VE is equal to dE upon T. Therefore, velocity ratio VR is equal to VE upon VL, that is equal to dE upon T upon DL upon T, or VR velocity ratio is equal to dE upon DL. Thus, the velocity ratio is also defined as the ratio of the displacement of the effort to the displacement of the load. And dear students, this point is very important. The velocity ratio is also defined as the ratio of the displacement of the effort to the displacement of the load. A machine in which the displacement of load is more than the displacement of effort will have the velocity ratio less than 1, and such a machine gives the gain in speed because load is moving at a faster rate. On the other hand, if the velocity ratio of machine is more than 1, that is, the displacement of load is less than the displacement of effort, the machine acts as a force multiplier. The velocity ratio of a machine is 1 if the displacement of the load is equal to the displacement of the effort. Such a machine generally changes the direction of the effort. Unit. Since the velocity ratio is also the ratio of two similar quantities, so it has no unit, just like MA, that is the mechanical advantage. Fifth point, work input. The work done on the machine by the effort is called the work input. That is, work input is equal to work done by the effort. Coming to the next, that is work output. The work done by the machine on the load is called the work output. That is, work output is equal to work done on the load. Efficiency. Efficiency of a machine is the ratio of the work done on the load by the machine to the work done on the machine by the effort. In other words, efficiency is the ratio of the work output to the work input. It is denoted by the symbol eta. Thus, efficiency is equal to work output upon work input. But efficiency is usually expressed as a percentage. So we may write efficiency eta is equal to work output upon work input into 100%. The unit, it has no unit since it is also the ratio of two similar quantities, that is work. Please remember the presence of friction and weight of the moving parts of a machine of a given design have no effect on its velocity ratio but decreases both its mechanical advantage and efficiency. Coming to the next, that is principle of a machine. When energy is supplied to a machine by applying the effort, it overcomes the load by doing some useful work on it. The point at which the energy is supplied to a machine by applying the effort is called the effort point, and the point where the energy is obtained by overcoming the load is called as the load point. So, input energy is equal to work done at the effort point. That is, input energy is equal to effort into displacement of the point of application of effort. Now, output energy is equal to work obtained at the load point. Therefore, output energy is equal to load into displacement of the point of application of load. For an ideal machine, output energy is equal to input energy. The useful work done by a machine, that is output energy, can never be greater than the work done on the machine, that is input energy. Otherwise, it will violate the principle of conservation of energy. Therefore, no machine can ever have efficiency greater than 1, that is more than 100%. Coming to the next point, it is ideal machine. An ideal machine is that in which there is no loss of energy in any manner. Here, the work output is equal to the work input. That is, the efficiency of an ideal machine is 100%. Actual machine. In an actual machine, the output energy is always less than the input energy, indicating that there is some loss of energy during its operation. The loss in energy is mainly due to the following three reasons. First, the moving parts in it are neither weightless nor smooth or frictionless. Second, the string in it, if any, is not perfectly elastic. And third, its different parts are not perfectly rigid. Please remember the energy lost in overcoming the force of friction between the moving parts of a machine is the most common type of loss of energy in it. If a machine is 80% efficient, it implies that 80% of the total energy supplied to the machine at the effort point is obtained as useful energy at the load point. The remaining 20% of the energy supplied is lost in overcoming the force of friction, etc., and it appears as heat energy in its different parts. As a result, they get heated up. Coming to the next point, relationship between efficiency, that is eta, mechanical advantage, and velocity ratio. Suppose a machine overcomes a load L by the application of an effort E in time t. Let the displacement of the effort be dE and the displacement of the load be dN. Then work input is equal to effort into displacement of effort, so E into dE. Work output will be equal to load into displacement of load, that is L into dN. So by definition, efficiency, that is eta, is equal to work output upon work input. So from equations 1 and 2, eta, efficiency, is equal to L into dL upon E into dE. So that comes to L upon E into dL upon dE. That is equal to L upon E into 1 upon dE upon dL. But L upon E is equal to MA, that is machine advantage, and dE upon dL is equal to velocity ratio. Therefore, efficiency eta is equal to MA, that is machine advantage, mechanical advantage upon VR, that is velocity ratio, or mechanical advantage is equal to velocity ratio into efficiency. Please remember this particular relation. Thus, the mechanical advantage of a machine is equal to the product of its efficiency and velocity ratio. Remember, for an ideal machine, which is free from friction, etc., work output is equal to the work input So the efficiency is equal to 1 or 100%, and the mechanical advantage is numerically equal to the velocity ratio. In actual practice, the mechanical advantage for all practical machines is always less than its velocity ratio. That is, mechanical advantage is less than velocity ratio, or the output work is always less than the input work, so the efficiency is less than 1, that is, eta is less than 1 due to some loss of input energy against friction, etc. Now, coming to the next, that is levers. I suppose levers is not a part of the syllabus, so we shall skip this point out. So we don't read about levers here because that's not there now as per the reduced syllabus. So kinds of levers, nothing, we don't have this. So I suppose we should go ahead fast. So don't worry, we will not take the syllabus. It is not there for you. We directly come to the next section, that is pulleys. So 3.8 pulley. You can look at the image there, the diagram 3.20, that is 3.20A and B, shows a simple pulley. It is a metallic or wooden disc with a grooved rib. A string or rope is passed around the groove at the rib. The disc rotates about an axle passing through its center. The axle is fixed rigidly to a frame by means of nails. So either a single pulley or a combination of two or more pulleys fixed in a frame is called as a block, while the string, that is rope or chain, that winds around the pulleys in different blocks is known as tackle. A single pulley can be used in two ways. First, as a fixed pulley by keeping its axis of rotation fixed in position, and second, as a movable pulley without keeping its axis of rotation fixed, that is, keeping the whole frame movable. Coming to the next, single fixed pulley. A pulley which has its axis of rotation fixed in position is called as the fixed pulley. Figure 3.21 shows a single fixed pulley in which the axle is fixed to a rigid support and an inextensible strong string of negligible mass passes around the grooved rim of the pulley. One end of the string is connected to the load L, while the effort E is applied at the other free end of the string. Both the load L and the effort E act downwards. The tension throughout the string is T, that is same upwards. This type of pulley is used for lifting a small load, such as a water bucket or a basket. Note, when the string is pulled, it is the friction between the string and the surface of the rim of the pulley which rotates the pulley. Now, mechanical advantage, velocity ratio, and efficiency of a single fixed pulley. If we neglect the mass of the string, the friction at the axle, or in the pulley bearings, then in the balanced position of the load, we have L is equal to T and E is equal to T when pulley is not rotating. So from equations first and second, E is equal to L. So if tension is not same throughout the string will then move even when the pulley is not rotating. Thus, in the case of single fixed pulley, ideal case, the effort needed to lift a load is equal to the load itself. In figure 3.21, for example, L is equal to 10 kgf or 98 newtons and efficiency is equal to 98 newtons. In actual practice, there is always some friction at the axle or in the pulley bearings, so the effort needed is little more than the load to be lifted. Now, mechanical advantage is equal to load upon effort, that is equal to T upon T, that is equal to 1. Thus, in this arrangement, there is no gain in the mechanical advantage. If the point of application of effort E moves a distance d downwards, the load L also moves the same distance d upwards. That is, if dE is equal to d, then dL is equal to d. Therefore, velocity ratio is equal to dE upon dL, that is equal to d upon d, that is equal to 1. Hence, efficiency eta is equal to mechanical advantage upon velocity ratio, that is equal to 1 or 100%. In actual practice, efficiency is always less than 100% because of some friction at the axle or in the pulley bearings. Now the question arises, when there is no gain either in mechanical advantage or in speed, why is then a fixed pulley used? A fixed pulley is used only to change the direction of the effort applied. That is, with its use, the effort can be applied in a more convenient direction. It is difficult to apply the effort upwards to lift a load up directly, but it becomes easier with the help of a fixed pulley because the effort can be applied in the downward direction to raise the load up. Further, to apply the effort downwards, one can conveniently make use of his own weight also for the effort. Coming to the next, a single movable pulley. A pulley whose axis of rotation is movable, that is not fixed in position, is called as a movable pulley. Single movable pulley suspended by passing an inextensible string of negligible mass around its grooved rim. The load L to be raised is suspended from its axle. One end of the string is tied to a hook H at a rigid support and the effort E is applied at its free end. The tension T acts on the string on both sides of the pulley as shown in the figure 3.22. You can have a look at it, close look at it. Now, coming to the next, mechanical advantage, velocity ratio, and efficiency of a single movable pulley. In the figure 3.22, if we neglect first the friction in the pulley bearings or at the axle and the weight of the pulley and the string, the load L is balanced by the tension T in two segments of the string, and the effort E balances the tension T at the free end. So, L is equal to T plus T, that is equal to 2T, and E is equal to T. So, from equations 1 and 2, E is equal to L upon 2. Thus, using a single movable pulley, the load can be lifted by applying an effort equal to half the load, that is, in ideal situation. That is, the single movable pulley acts as a force multiplier. Now, mechanical advantage is equal to load upon effort, that is L upon E, or mechanical advantage is equal to 2T upon T, that is equal to 2. When the free end of the string is pulled up by the effort through a distance 2D, the load is raised up through a distance D. The reason is that the segment of a string on both sides of the pulley moves up by a distance d. That is, if dE is equal to 2d, then dL is equal to d. Therefore, velocity ratio is equal to distance moved by the effort, that is dE, upon distance moved by the load, that is dL. Or velocity ratio is equal to 2d upon d, that is equal to 2. Hence, efficiency eta is equal to mechanical advantage upon velocity ratio, that is equal to 2 upon 2, that is equal to 1, or 100%. For an actual single movable pulley, due to friction in the pulley bearings or at the axle and the weight of the pulley and the string, the effort needed to lift up a load L will be more than L by 2. So, the mechanical advantage will be less than 2 since the velocity ratio will remain 2, hence the efficiency will be less than 100%. Now, way to change the direction of effort using a movable pulley. With a single movable pulley, the effort is to be applied in the upward direction. However, it is inconvenient to apply the effort in an upward direction. Therefore, a movable pulley A is used along with a fixed pulley B to change the direction of the effort as shown in the figure. The load is attached to the axle of movable pulley A and the effort is applied in the downward direction at the free end of the string passing over the fixed pulley B. One can also use his own weight as effort, which will be quite convenient. Note: the mechanical advantage and the velocity ratio of the arrangement shown in this figure 3.23 remain same as that of a single movable pulley. Please have a closer look at it. Now, going ahead, let's compare the single fixed pulley and a single movable pulley. Single fixed pulley is fixed to a rigid support, whereas the single movable pulley is not fixed to a rigid support. Single fixed pulley, its ideal mechanical advantage is 1, whereas the ideal mechanical advantage is 2 for a single movable pulley. The velocity ratio is 1 in single fixed pulley, whereas the velocity ratio is 2 in a single movable pulley. Fourth, the weight of pulley itself does not affect its mechanical advantage in case of single fixed pulley, and in case of single movable pulley, the weight of pulley itself reduces its mechanical advantage. In a single fixed pulley is used to change the direction of effort from upwards to downwards. Single movable pulley is used as a force multiplier. The load moves in a direction opposite to that of the effort in a single fixed pulley, whereas the load moves in the direction of the effort in a single movable pulley. Now let's talk about the combination of the pulleys. Combination of pulleys. When a heavy load is to be lifted or shifted from one place to another, we require a pulley system of mechanical advantage much more than two, so a single movable pulley is not enough. A combination of several pulleys with one or more strong, thick string or rope is then used. The combination can be made in two ways. First, using one fixed pulley and several movable pulleys attached to the same rigid support, and second, using several pulleys in two blocks, of which lower block is movable and upper block is fixed, known as the block and the tackle system. Now, coming to the first, using one fixed pulley and other movable pulleys. You can see this image figure 3.24 shows a system of three movable pulleys A, B, and C used with a fixed pulley, that is D. Each movable pulley is attached with a separate string. The tension is same in one string, but it is different in different strings, being maximum in the string of the pulley to which the load is attached. So, the mechanical advantage in equilibrium, effort E is equal to T3. The two segments of the string passing over the pulley A supports the load L. Therefore, tension T1 in this string is given as 2T1 is equal to L, or T1 is equal to L by 2. Similarly, the two segments of the string passing over the pulley B supports the tension T. So tension T2 in this string is given as 2T2 is equal to T1, or T2 is equal to T1 upon 2, that is equal to L upon 2 square, using equation 1. Similarly, the tension T3 in the string passing over the pulley C can be given as 2T3 is equal to T2, or T3 is equal to T2 upon 2, that is equal to L upon 2 cube using equation 2. Now from this equation 4, load L is equal to 2 cube into T3. Now from equations 1 and 5, E is equal to L upon 2 cube. Hence, mechanical advantage MA is equal to load upon effort. That is equal to 2 cube into T3 upon T3. That is equal to 2 cube. In general, if there are n movable pulleys with one fixed pulley, the mechanical advantage is then MA is equal to 2 raised to n. Let's understand the velocity ratio. As one end of each string passing over a movable pulley is fixed, so the other end of the string moves up twice the distance moved by the axle of the movable pulley. If the load L attached to the pulley A moves up by a distance x, that is, dl is equal to x, the string connected to the axle of the pulley B moves up by a distance 2 into x, that is equal to 2x. The string connected to the axle of the pulley C moves up by a distance 2 into 2x, that is equal to 2 to the power 2x, that is 2 square x. And the end of the string passing over the fixed pulley D moves up by a distance 2 into 2 square x, that is equal to 2 cube x. That is the effort E moves by a distance 2 cube x, or dE is equal to 2 cube x. Therefore, velocity ratio is equal to distance moved by the effort dE distance upon distance moved by the load dL. That is 2 cube x upon x is equal to 2 cube. In general, if there are n movable pulleys connected to a fixed pulley, then velocity ratio VR is equal to 2 raised to n. Efficiency is equal to mechanical advantage upon velocity ratio, that is equal to 2 raised to n upon 2 raised to n, that is equal to 1, or 100%. Note that the efficiency of this arrangement is 100% only in an ideal situation. In actual practice, both the weight of the pulleys and the string and the friction between the bearings of the pulleys reduce the mechanical advantage, and so the efficiency becomes less than 100%. Coming to the next, using several pulleys in two blocks, that is block and the tackle system. In this system of pulleys, two blocks of pulleys are used. One block, that is upper, having several pulleys, is attached to rigid support, that is fixed, and the other block, that is lower, having several pulleys, is movable. This arrangement is called the block and the tackle system. The number of pulleys used in the movable lower block is either equal to or one less than the number of pulleys in the fixed upper block. A strong, inextensible string or rope of negligible mass passes around all the pulleys. One end of the string is attached to the hook of the lower block. If the number of pulleys in the upper block is more than that in the lower block, or it is attached to the hook of the upper block, if the number of pulleys is equal in both blocks, so as to apply the effort in the downward direction. Figure 3.25 shows a block and tackle system of 5 pulleys in which one end of the string is attached to the hook of the lower block, while figure 3.26 shows a block and tackle system of 4 pulleys in which one end of the string is attached to the hook of the upper block. The load L is attached to the movable lower block, and the effort E is applied at the free end. So you can look at this image, figure 3.25 on the left hand side, where the block and the tackle for 5 pulleys is being shown, and on the right hand side you have figure 3.26 with block and tackle for 4 pulleys. So the load N is attached to the movable lower block and the effort E is applied at the free end of the string. The tension along the entire length of the string is same and is denoted as capital T. Now, mechanical advantage. In figure 3.25, the tension in the 5 segments of the string supports the load L. Therefore, L is equal to 5T and E is equal to T. Therefore, E is equal to L upon 5 and mechanical advantage is L upon E, that is 5T upon T, that is equal to 5. Similarly, in figure 3.26, the tension in the 4 segments of the string supports the load L. Therefore, L is equal to 4T and E is equal to T. Therefore, E is equal to L by 4 and mechanical advantage is equal to L upon E, that is 4T upon T, that is equal to 4. In general, if the total number of pulleys used in both the blocks is N and the effort is applied in the downward direction, then the tension in the N segments of the string supports the load. Therefore, L is equal to NT and E is equal to T, or E is equal to L upon 9, L upon N. Thus, the effort required to balance the load is E is equal to load upon N, that is number of pulleys. Thus, in a block and tackle system, the effort gets multiplied N times, where N is the total number of pulleys in the system. It therefore acts as a force multiplier. Hence, mechanical advantage MA is equal to load upon effort, that is equal to NT upon T, that is equal to N, that is equal to total number of pulleys in both the blocks. Now, coming to the next, that is velocity ratio. In a system of N pulleys, if the load moves up through a distance D, each segment of the string supporting the load is loosened by length D. So the effort end moves through a distance ND. That is, if DL is equal to D, then DE is equal to ND. Therefore, velocity ratio is equal to DE upon DL, that is equal to ND upon D, that is equal to N. Thus, the velocity ratio is always equal to the number of strands of tackle or number of sections the string supporting the load. Efficiency, eta, is equal to MA, that is mechanical advantage, upon VR, that is velocity ratio, that is equal to N upon N, that is equal to 1 or 100%. The efficiency is 100% only in the ideal situation. But in actual practice, there is always some friction in the bearings of the pulleys, and the weight of the string, along with the weight of the lower block with pulleys, is not negligible. So the mechanical advantage decreases, and hence the efficiency decreases. Note, the pulley system is only a force multiplier, and just like other machines, there is no gain in energy. This can be seen as follows. The work done by the effort or the input energy is equal to effort into distance moved by the effort. That is equal to E into ND. That is equal to NED. The work done on the load or the output energy is equal to load into distance moved by the load. That is equal to L into D. That is equal to NE into D. That is equal to NED. Since mechanical advantage is L upon E, that is equal to N, thus there is no gain in energy. Now, coming to the next, that is effect of weight of pulleys on mechanical advantage, velocity ratio, and efficiency. Consider a system of N pulleys. Let W be the total weight of the lower block along with the pulleys in it. In the balanced position, E is equal to T and L plus W is equal to NT, or L is equal to NT minus W, that is equal to NE minus W. So mechanical advantage is equal to L upon E, that is equal to NE minus W upon E, that is equal to N minus W upon E. Thus the mechanical advantage is less than the ideal value N. The velocity ratio does not change, it remains N, that is VR is equal to N. Hence efficiency eta is equal to mechanical advantage upon velocity ratio, that is equal to N minus W upon E upon N, or eta is equal to 1 minus W upon NE. Thus, the efficiency is reduced due to the weight of the lower block of pulleys. More the weight of the lower block, less is the efficiency. For greater efficiency, the pulleys in the lower block should be as light as possible, and the friction in the bearings of the pulleys should be minimized by the use of the lubricants. These examples you might have already solved. So we have finished off reading off for this chapter. So please ensure that on the way to the exams also you can keep on listening to these videos. Okay, we shall definitely in few minutes try to catch up again for maybe a paper solving session or maybe the reading for another chapter. Let's see how it goes. I know it's already 15 minutes past 12, but you have your exams tomorrow. So we shall be studying till the last minute. Now, there are people who believe not to study till the last minute, but it's always better to keep on reading. Kavya, you're so late today, but if you're not feeling sleepy, you can still hang on and listen to another chapter that we shall be streaming very shortly. And also, we have 3 paper solving sessions which have been scheduled maybe tonight or maybe tomorrow morning. Let's see how it goes. So don't sleep. Let's hang on and go to the next chapter. See you in 15 minutes. See you soon. Maybe lesser than 15 minutes if possible.